So with all that in mind, I would like to introduce our first speaker, Professor Thomas Küstner. Dr. Küstner is the Chair of Medical Imaging and Data Analysis at the MEDUS lab at the University Hospital of Tübingen in Germany. He received his PhD from the University of Stuttgart in Germany in 2017 and later joined the School of Biomedical Engineering and Imaging Sciences at King's College London. In 2023, Dr. Küstner was appointed a professorship at the University Hospital of Tübingen to study data engineering and advanced processing for medical imaging modalities. His research group actively works on artificial intelligence-enabled multi-parametric and multimodality medical imaging methods in acquisition and in reconstruction, and the automated analysis of clinical and epidemiological studies. Dr. Küstner is particularly focused on MR-based motion imaging, correction and reconstruction, and the advents of artificial intelligence in MRI. Dr. Küstner, I'm honored and excited to pass it over to you.
Thanks a lot for the very kind introduction, and thanks a lot for the invitation to guide you through a little bit our MERLIN framework that I want to show you now in the next couple of slides. So I hope that you can see my slides. So I'm going to talk you through the MERLIN, the Machine-Enhanced Reconstruction Learning and Interpretation Networks. So what's behind that? It's primarily a framework for MR image reconstruction. So considering that we are acquiring our undersampled case-based data, we want to come back to our image. Obviously, this involves that you have different solutions at your disposal: compressed sensing, low rank, and deep learning based methods. What all they have in common here is to solve the linear inverse problem. And this linear inverse problem entails some forward encoding operator that can be comprised, depending on your imaging application, by some motion, call sensitivity maps, Fourier transformation, and obviously the underlying sampling that you have chosen. So that means for the solving this linear inverse problem, we have here usually two parts that we need to consider. One is the data consistency term, and the other one is a regularizer term with often a tunable parameter. This can be also multiple regularizer terms. And in the following of the talk, I will only focus on deep learning-based solutions that are trying to learn this regularizer here. So the learning objectives here are to introduce you to the different flavors of the MR reconstruction concepts in very, very brief, and to show you some of the key architectures and building blocks that one can use to solve this problem. Which I will, however, not cover is going into depth of all the different flavors of nonlinear model-based reconstruction, the different learning strategies, database composition, domain shifts, what happens if you couple different applications into joint multitasking networks, or what do you need to do to make your network application specific. I would like to refer you here to this very nice book, and where we also have a book chapter about this in this book that gives you a little bit more insights for that. So starting off, we have different flavors of image reconstruction networks that we can have a look at when we're working on pure image domains, so image-to-image networks. We can have case-based to image networks, and we can have this so-called physics-based unrolling network with different flavors of case-based to case-based, or image and case-based in hybrid networks, or which we are more often seen in this physics-based network are this unrolled optimization, which I will also go over in the next few slides. Or you can also have deep image priors or some distributional learning. So to give you a little bit more of an in-depth view of what this means for the image enhancement, as a first pass, you have your undersampled case space. You have your joint encoding operator gives you your initial image, and you're learning a neural network that reconstructs then your image, or does an image denoising task. For the physics-based unrolling networks, we can have the initial image as an input, and then several unrolls of these neural networks with also included data consistency steps that use now the undersampled case space and call sensitivity maps to ensure data fidelity. You could also work directly on the case-based data itself. So you're going from the undersampled case space to a fully sampled case-based data, again, similar to kind of like a grappa reconstruction where you now learn these grappa kernels. You can also perform this in a plug-and-play prior fashion or as a deep image prior fashion, where you offload your learning phase of your regularizer. This can be specific for a certain task or can just be specific to modeling the certain noise distribution that you're expecting. And then you can plug this into any kind of reconstruction that you favor, either a deep learning-based network, or this can also be a conventional reconstruction. Lately, we've also seen the advance of distributional learning methods, for example, where you have here this diffusion network, where you gradually denoise from a completely noisy image to the noise-free image. And you can also model in there then data consistency into the individual denoising steps by various flavors of bridges, Schrödinger bridges, and so forth, that allow you to still ensure the data fidelity. So with all these different possibilities in mind, and also since our group has been working extensively along these lines of these different methods and also in collaboration with others, we have seen that it is sometimes quite easy to fall into the trap that you make wrong assumptions and have a bug in your code, and then think you have like found the next great thing, but actually you have just introduced errors in your code. And in order to avoid that, we have started then putting all our codes together in the so-called MERLIN package, which we have to develop together with our partners of the Technical University of Munich. So this is a compilation of different modules that contain different aspects of the code, and that should hopefully be plug and play for your application that you have in mind. So we've built this up on top of PyTorch and TensorFlow, the two most common backends for deep learning algorithms. And I will show you in the next few slides how easily they integrate in there and what is contained in each of these individual modules. There's also further material for you to check out. We have covered this MERLIN framework and different flavors of it, especially on the focus of cardiovascular imaging in 3 member-initiated tutorials at ISMRM, and all the materials are still available online on this website, so feel free to check this out here as well as further material. So the MERLIN contains in principle 3 packages and 1 additional package that you need for loading. And the first package is the so-called MERLIN Py, which just summarizes a lot of pure Python functions, like a data pipeline that you need to fed through your input data through the network, transform functors for doing the sampling for you, for doing some data augmentation strategies, some conventional reconstruction methods that you want to use, your BART or your iterative sense reconstructions there, and also some metrics that allow you then at the end to quantify quantitatively the image quality that you obtained. The MERLIN TH is now the MERLIN package that builds up top of PyTorch, and has all these PyTorch functions of the layers, losses, models, and optimizers. I will go through that in the next few slides. And then there's the MERLIN TF that builds up on top of TensorFlow and Keras in a similar fashion as the PyTorch functions. However, since these are all functions, sorry, that was advancing. Since these are functions that are building on top of core functionalities that are usually written in CUDA and C++, we're using the optox framework as additional means to integrate these functionalities of the layers and operators. So what does this mean? The optox is now a selection of these compiled and device-specific functions, depending on the hardware that you're using it, for the specific CUDA version, for the specific Python version that you're using with the different libraries. You always need to recompile your environment and your CUDA code. And to have this very efficiently implemented, we have these CUDA and C++ implementations in the optox environment. And they also have integrated unit tests for continuous deployment, so that we can continuously monitor and see that our code that we have developed is still performing the same way, even if we add functionalities later on. We include then wrappers to these high-level interfaces of MERLIN Pi, MERLIN TH, and MERLIN TF. So for you as an end user, you only need to take care of one-time installing Optox, and then you don't need to care about this package anymore. It is completely oblivious to you. So you're just calling your MERLIN TH, your MERLIN TF functions, and they will in the backend then call these respective Optox functions. And in this Optox, for example, there is then, just as one example, the GPU NUFT that allows you then to do some non-Cartesian reconstructions. So the structure, for those who are a little bit more interested and are also willing also to help out in coding, and we are always looking for participation of someone to step in and implement then the functions that are still missing here. So we have some source files that are this very much linking of this tensor, the header to the operators, which are the actual implementations. And then we have these mentioned wrappers to the Python, PyTorch, and TensorFlow cases together with the respective unit tests. So the next package I want to talk you through is the different sampling trajectories that we have in there. We have different Cartesian sampling flavors that you can try out, regular undersampling, Poisson undersampling, Gaussian or Vista undersampling with different parameterization of these codes respectively, and also some radial and spiral sampling trajectories, also with regridding to a Cartesian grid if necessary. The next module is the so-called modules package, which contains a lot of like larger scale operators, and one common operator, which I've also showed you in the first slide, is this encoding operator. And this can be, depending on your data, for example, be a multi-coil operator in a forward and into a joint direction. So you don't need to care anymore about how is this done with the Fourier transformation, call sensitivity maps. You just define this layer and you just hand over then the call sensitivities, the K-space, and your sampling mask, and then the layer does the rest for you. If you want to integrate, for example, a motion correction, so you want to do a warping and have a layer that is also differentiable, so you can also do optimization through this layer in the back propagation path. We also have the layer here for you. This is then the multi-coil motion forward operator. You could also work on single call data, then it's quite obvious. You just skip then the multi-call, you just have then the motion forward or just the forward operator. You can check out all the different flavors in our GitHub repository there. Similar example for the GPU NUFT. So you hopefully have seen now the theme by we just replacing then always the key buzzword and opting then for the same notation style. So with that, you should hopefully have easy integration into your methods. The modules package also contains different losses, optimizers, and other reconstructional frameworks. I'm just listing here you a few, like SSIM. We have real and complex valued variants of the mean squared error, of the mean absolute error, PSNR, VGG losses. Other more specific optimizers that they are also targeted to specific architectures, like the block atom optimizer for the fields of expert regularizer, so the variational neural network. And also you can plug into your different reconstruction codes, like we have a conventional iterative sense in there, and also you can call the BART package, which last denoted as Merlin's BART. So if you want to integrate that, and we're also in discussion with the BART people, how to integrate their functionalities of deep learning better together with the Merlin package, so that we have an easier integration of both of these frameworks. But this is future releases to come. This is not yet there. So just to give you a little bit of an example, if you want to perform a simple iterative sense reconstruction, I've already showed you this MRI operator. You just define this for the torch package, so multi-coil forward operator. Then it's as simple as solving the iterative sense by these two lines of code. I say my iterative sense layer is just this one. I just give it my forward and my adjoint operator. I just define a few other parameters like the number of iterations I want to run this. And then I just plug in my K-space, my mask, my call sensitivity maps. And at the end, I just match everything to be a NumPy array. I can still leave it to be as a tensor. It's just for illustration purposes. And you can also see, like, if you wanna, if you wanna go to TensorFlow or Keras, you just replace then the Merlin Keras or the Merlin TH by Merlin TF.Keras. And we have tried to stay as similar as possible to the TensorFlow and respective PyTorch implementations. So it is also easy for you to plug in the different structures of the layers. And this will also, you see that's later when we go over the layers in operations. Next is the data pipeline, and this is still currently work in progress because this is often very much application dependent, but I want to show you a little bit what we have envisioned for this, that you get an easy means of importing your whole your whole database cohort, and then that's a specific splitting into training, validation, and test based on certain criteria, obviously, that you want to avoid then overfitting of your network. And also then depending on the different learning strategies that you have available, from a supervised learning over to a self-supervised learning, or if you integrate more human in the loop, like an active learning or reinforcement learning or federated learning, that all these different flavors are covered by your database pipeline. So it will be a compilation of different applications that are increasing then over time, but again, work in progress at the moment. Next is the layers and operations, and the very simple thing here is the convolutional block that we have tried to make as the simple combination of a convolution, normalization, and activation. And this is one entity, but you can use as you would like it, but this is what we have often seen in various of the models that are currently performing deep learning-based image reconstruction. So you can have like a concession of this convolutional blocks here. But again, I want to step you through now these individual parts here, what we have in the Merlin framework. The first is the convolutional layer. So if you're just performing real valued convolution, this is exactly the same as you would do with a normal implementation. There's no need for you using now the Merlin package. Obviously, this is already covered by PyTorch and TensorFlow. But just to give you a little bit of a background, you can have different padding of your feature maps, depending if you have a full padding or a same padding of the output. Also, the striding of the kernel over your input feature maps can be different. And obviously, you can also have dilated convolutions where you have the kernel being spreading out further, or deformable convolutions, which we're currently implementing. But why I'm telling you now this, because the most important thing here is to consider that we are always working with complex valued data. And so our convolutions are complex valued convolutions following this paradigm. So under the hood, you just call the Merlin TF layers and the Merlin TF convolutional layers, and they are complex valued convolutions. So considering then the real and imaginary parts of the respective input image and the kernels in this fashion. Same flavor, batch normalization, instance normalization, and layer normalizations are implemented, and we have always fallback. So if you still decide to work with our Merlin layers for running this, and you input then some real value data, we're just resorting back to the PyTorch implementation without you having then overhead. So you could just always write our Merlin functions for that. And then you can later on decide if you want to plug in real value data or complex value data, or data as a two-channel real variant, which I will show you also in a second. Same goes also for the activation functions, and you have different flavors for that as well, like the conventional ReLU, where we see often used, but then also the complex variants that you have for like a complex ReLU and the mod ReLU. And I'm just showing you here the magnitude and phase responses of these activation functions. For the real valued one, you only have the magnitude response here. Same goes for sigmoid, normal sigmoid. We have a complex valued version as a separable sigmoid or siglog functions. And there are many, many more like cardioid, iGaussian, IRBF, and so on and so forth. So feel free to check out whatever serves your purpose. You also have in there downsampling layers, might sound not so obvious, but especially for a max pooling operation, you need to consider where you're sampling and where the sampling points are coming from to perform then the max pooling or an average pooling in a complex value domain. So you're deciding this based on a magnitude or within this feature map, and then sample like the respective locations. Again, very seamlessly for you integrated into the MERLIN package using then the Optox implementations in the background. So to show you a little bit now how this all comes together, I want to step you through a use case of physics-based unrolling, and where we also have like then this example code then in the GitHub repository. So again, this is like neural networks in over several iteration steps, and you have then data consistency and a learnable regularizer. So written this in a little bit of a different sense. You have here your data consistency that you're trying to fulfill, and you try to learn your learnable regularizer. You consider this as a gradient descent optimization. So you're trying to optimize your model parameters over different gradient steps and learn these model weights then there. And this is the CNNet example as a very, very straightforward example of what you can do. So you have here, learnable regularizer and intermittent data consistency blocks. They're just one-liners of code. So you have a unit already there. You have a DC layer already there, as similar as before with the iterative sense. You just plug in all the information, and then you just stack them one to one after the other. So this is what we call in our lower level problem of defining then the architecture. And within this unit, obviously, you have different flavors of performing then this max pooling operations, convolutional layers. We also have in this special case, since we have a dynamic dimension, also a spatial and temporal convolution, which is also in the MERLIN package. And then you have your normalization and activation layers there as well. And then on the higher level problem, you decide then at the end for your training loss that you want to use. In this case is a complex valued MSE. And just to give you some examples how this looks like, if you perform this reconstruction on a single breath hold acquisition or on a 2-minute free breathing acquisition, you can get very good image quality that is comparable to the conventional 2D cine acquisition, but in way, way shorter scan time. So as a second use case, as a very simple toy example, and this is also provided within the GitHub repository, is you can decide between a complex valued or real valued image reconstruction. So meaning your input can be either a complex value tensor X, or you already have stuck your complex value data into a real and imaginary component. Meaning you can plug this in now to this physics-based unrolling network as the unit before. Here it's a ResNet structure with a data consistency block. And then, or you can run this as an image enhancement network. So meaning you plug in your magnitude of, sorry, oops, that was going too fast. You plug in the magnitude of your image. What this means is that you have these either real valued convolutions or your complex valued convolutions, depending on the input of the data and depending on if you're performing this as a complex valued network or as a more image enhancement network with a real valued input. But you see from the interfaces, they look very much alike. So this is just tf.keras layers conv2d, and this is MERLIN tf keras layers complex conv2d. And as mentioned, you can also use this layer and define this as a complex valued layer. If we identify that you're just sending through real valued data, we resort back to this real valued implementation of it. And these are then the different outputs that you get for running this through these different networks and these different flavors. So what we have seen is that this can be very similar. However, you can have a performance improvement of the complex valued models because they consider the complex valued relationship between within the data instead of like just stacking them in a two-channel real value variant. You can do a better task if you consider this complex valued relationship. So feel free to try this out in your own methods. We also compared, since we have these two different backends, what happens if you use PyTorch or TensorFlow. And this is still ongoing investigation. But for now, it's like a very dense figure and a lot of graphs. But the takeaway message is TensorFlow performs better than PyTorch. The reason that we have so far identified for that is that the TensorFlow integrates complex valued operations since the beginning of the development, and PyTorch has just brought in the complex valued tensors starting from version 0.6, if I'm not mistaken, and gradually improving this now over time. So the improvements are diminishing over the different versions of PyTorch. But just pay attention if you're using an older version of PyTorch that has just recently implemented the complex valued operations, you may see a performance drop in comparison to TensorFlow networks. So also, if you're refactoring code from a public repository of a TensorFlow implementation to a PyTorch, you need to consider which PyTorch version you're using because that will have impact on your overall performance. So I've showed you a lot of like different examples, but to give you some guidance, we also have here in our GitHub repository different notebooks that allow you to go to dive a little bit more deeper into all the different implementations. So there are a lot of like Jupyter notebooks that let you explore the different activation functions, that let you explore these differences of real valued, complex valued operations of the different convolutional layers. So you have already there a little bit of a playground to test it out and to see how this is actually implemented, hopefully helping you to easier integrate this into your desired solutions. So with this, I want to conclude. I hope you saw that the MERLIN package can be quite helpful to help you working with complex valued and high dimensional data. It's a collection of different operators that are primarily MR specific with data processing and certain functions. And we have integrated this with existing backbones like PyTorch, TensorFlow, Keras, and are further integrating this with other frameworks like the BART toolbox and also Torch.io for the data pipeline. So without reinventing the wheel here. And we also have a collection of different models and unit test operators in it that allow you to test then the functionalities of the whole model. You can just simply install it by a pip package as written down here, or just follow the installation instructions on GitHub. And then it's as simple as importing this package here. We're currently working on a new release with some more functionality. So it is a continuous development. So feel free to also contribute to the MERLIN package, raise some issues or pull requests if you have some ideas for features that should be integrated. And with this, I would like to thank you very much for your attention, and I'm happy to answer any questions.